if you recall, in the simple basic Neopixel sketch that we made, I was independently creating variables. An R for the red value, G for the G value, B for the blue value, and then calling set pixel color, pixel strip color, red, green, blue value. This is very specific and very direct and very wasteful and very confusing potentially as soon as you get to 2 pixels or 3 pixels, much less 12 or 300 pixels. I don't want, among other things, to need 3 different variables per pixel. One of the things you can do is you can use an array. And an array doesn't need to be large. An array can be something very small, like this, where I have declared an integer. I'm calling it strip map for a reason. It's not really a strip at the moment. This is one single variable with 3 elements, 0, 1, and 2, that will hold 3 integers. And I'm going to use the first one for the red value, the second for the green value, and the third for the blue value. And I can reference these in my program by calling strip map 0, 1, or 2. And then I am immediately just simply setting a pixel, pixel 0, to be the color referenced by whatever the red value in strip 0 is, and the green in strip map 1, and the blue in strip map 2. And this works just fine. If I change, let's say, the green value to be 255, and I run the program, pixel 0 green turns on. By using this array, I can have completely independent control of the red and the green and the blue. I can remap these numbers independently on demand, and then when I'm ready, I can send them to the strip. At the moment, this is only 1 pixel, and that's not terribly useful for what we want to do. So let's say we had a strip of Neopixels that was 2 elements long. I can increase this from a 1-dimensional array to a 2-dimensional array with another square bracket. So now it's going to be a 2 by 3 dimensional array. It's going to be the equivalent of an Excel spreadsheet that has 3 columns and 2 rows. But I also need to initialize the rows and columns to be what the values are going to be. So the first row, row 0, is going to be 0, 255, 0. The second row is going to be, let's say, red. Again, in curly braces. And in order to collect all these together into the actual 2 rows by 3 columns, we need a second set of curly braces around them. This can be made a little more clear if we look at it like this. As far as C is concerned, this is the exact same thing. So we're starting an array, and this is column 0 in row 0, column 0 in row 1. And I can reference these. So down here, now we have 2 pixels worth of data. So if I specify row 0, it's still green. That was exciting. But if I change it to row 1, and anytime I want to, I can individually address these and change them. So strip map row 1, column 2, which is the blue value, equals 255. So now the array is going to be initialized with these values. And then later in the program, somewhere before I send the data out to the pixels, I decide that I want the blue on the second pixel, pixel 1, to be also turned on. I'm making no reference whatsoever to the red or the green pixel right now. I'm just directly addressing the blue. So what happens now? Red and blue together, peacefully coexisting. My bigger array is going to be 12 pixels, well, 12 rows. Still going to be 3 columns for the red, green, and blue. And I need to expand this so that there's 12 sets of initializations. I'm going to initialize everything to be off. And I'm going to put everything on one line. Pixel 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Curly, curly, semicolon. So in the next stage, what I'm going to do is I'm going to set the red pixel to show the CV, the blue pixel to show the PV, and the SP is going to be shown on the green pixel. I will write to this array as needed to update the current values, but I will only write that to the pixel strip and show the pixel strip on a much less frequent schedule of maybe a few dozen per second. Let's say 100 per second to start, and we will slow it down or speed it up as necessary. So, step 1. The Neopixels and the timing are pretty much in place. So, the beginning of the program is the Neopixel is connected to 6. There's 12 Neopixels. I have the first motor pot connected to A0. I have the second motor pot connected to A1. The push buttons for floor 1, 2, 3, and 4 have been mapped. We create the Neopixel. I'm creating an array of booleans. We only have 4 floors, but I'm creating an array that is 5 long so that floor 0 can be pretty much ignored. And we're just going floor 1, 2, 3, 4. So we can reference them directly as 1, 2, and 3, and 4. There is no floor 0 for now. The PID coefficients, set point, process value, and control value. The error, the integral. We're keeping the update rate as seconds for now, but that may or may not change. I don't want to change away from seconds in the code for the moment, because I can directly use the PID code from the demo in this program. However, for the purposes of keeping the timing straight, the period of the update PID loop is going to be measured in microseconds. So is the period between checking push buttons and the period between updating the Neopixels, all microseconds. The matching variable to the period is the timer, and this is the accumulated values. In setup, I'm initializing serial communications, I'm initializing the Neopixel. I am making the Neopixels a little bit brighter. It was 15 up until now, which is bright enough for my eyes, but on camera it's not as bright as I would like it to be. So it's actually 12% right now. Floor push buttons are inputs. These are those prototypes that I was talking about with functions. If these were not here, When the compiler goes through the program from top to bottom looking for errors, and it gets to loop, and I call update PID, if it has not seen function update PID yet, it will throw an error. But I don't want all of my functions to be at the top of the program. I want them to be at the bottom of the program. The way you get by that is by just letting the compiler know that the code for update PID does exist somewhere in the program. For now, it happens to be void. It doesn't return anything. It has no parameters. We're not passing it anything. All of the variables are global variables. So we're keeping it very, very simple. But then this matches at the end of the program the actual functions. Now the update PID function happens to be empty at the moment because I'm not running that code. I haven't integrated it. What I have done is create a function. Actually, let's go to the timing first. So in loop, and I don't expect loop to get much bigger than this. There are a couple of things that I'm doing as fast as possible. That's reading the analog feedbacks. This pot is temporarily going to be set point. This pot is temporarily going to be the process value. Actually, it's going to be always the process value, regardless of whether we're running it on the motor pot or running it from the elevator. Those I want updated as frequently as possible. The things that I want to update periodically are if the timer update for the PID, if the accumulated time for the update PID loop is greater than the PID update period that we've specified, then call the function, zero the timer, and temporarily, only for this tiny little video right here, I am printing PID exec time and the loop's most recent execution time. I'm duplicating this code for checking the push buttons much less frequently than we're updating the PID, and updating the Neopixels a little more frequently than we're checking push buttons, but less frequently than we're updating the PID. So we're keeping track of time, we're accumulating the time in the timer variables, and that's it. So far, this is all that's in loop, and there's not going to be a whole lot more to it later. By doing what I've done the way I've done it, loop is going to be very clear, very simple, and it really just organizes everything. So when it's time to check push buttons, we check push buttons and then jump back. When it's time to update the Neopixels, we update the Neopixels and jump back. And in between updating the Neopixels and the PID and the push buttons, we're just continuously reading feedback as quickly as possible. So what happens in the loops that we have right now? Well, I do have nothing in the PID loop, but I still have the function sitting there waiting to have the PID code copied into it. I am checking for the push button presses. So when this function is called periodically, it jumps down to the function that checks for push buttons. And if we read push button 1 and it's been pressed, it sets floor calls 1 to true. Lather, rinse, repeat for the other 3 floors. When it's then time to update the Neopixels, that code is a little tiny bit more complicated. I'm creating this array as a local variable to this function and initializing all of the colors, the red, green, and blue colors, to be zeros. Then check the PID values. So I'm setting strip map row number based on the Neopixel it is. So let's say the PID set point is 0. We're mapping that 0, which we expect to be a range of 0 to 100, to be 11 to 4. Because 0 is at the bottom of the Neopixel strip, and therefore is Neopixel number 11. 100% is near the top of the motor pot and is pixel technically 5, but there's a little bit of an interesting scaling issue, so I'm using 4 instead. So 100 ends up being 4. Since it is the set point that I'm mapping, I am mapping the green being column 1, the blue being column 2, and the red, which is the CV, being column 0. Set point and process value are both 0 to 100. The control value is minus 100 to positive 100, and actually works pretty well when I reference Neopixel 5. Point being, the set point is mapped to the green pixel, and then when the process value is mapped to the blue pixel, writing 255 to the blue part of that pixel will not overwrite the fact that set point was also on. So it's not going to change the green pixel to a blue pixel. It's going to turn on the green pixel, or the green LED of that pixel, as well as the blue LED of the same pixel. It's non-destructive. And I wasn't sure how I was going to do the floor call indication. But what I decided to do was this. When we update the Neopixel, we are going to go through the floor 1 through 4. Let's say that floor 1 is called. And let's say that the set point is 0. Those both reference the bottom pixel on the strip. So the set point would have turned on the last pixel, the bottom pixel's green LED. Assuming that it's only the green LED that is on, that the process value and the control value are at different locations, then when we get down to this for loop and we look at floor call 1, we're going to map to the pixel floor call 1 equals pixel 11. We're going to look at pixel 11 red value. If red value is off, we're going to set the red value to be 1/4 brightness. So it's going to be dim red. Same thing with the blue, the green. So if the green is off, then we will set the green to a dim green. And if the blue is off, then we will set the blue value to a dim blue. But if it was already on, and if set point is 0, then the green would be on. And the green would be on brightly at 255. Then what's going to happen in this is that green will remain bright green, but the red and the blue will be set to 1/4 red and blue, which effectively is going to give us a pale green on that pixel. So the pixel is going to look white with a greenish tinge. But if the floor isn't called and the set point is there, then it's going to be a bright green. And if nothing is there, then it's going to be black. So you can see that in the code that I'm currently running, where we have the set point, and if the set point is on pixel 0, and we press the floor 1 button, then that pixel will become a pale green. But if we move the set point away from that pixel, the set point is bright green and the indicator turns white. The same occurs if we have the process value on floor 4 and we press floor 4, then the blue process value will become a pale blue. So ideally this is going to be very clear in operation, but right now I'm just playing, so we'll see what happens. Meanwhile, in that main loop, where every time one of those timers is triggered and calls the function, it's also printing out the execution time of the program. If we look at the execution times, generally it's 1.7 milliseconds. And if we turn off the auto scroll so it's a little more readable, you can see that PID called PID, 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 PID. LED was updated once. PID, 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 PID. The push buttons were updated. More PIDs. The LED was updated. But realistically, this 1.7 milliseconds is partly due to the fact that I'm doing a lot of printing to the serial console. So if we just didn't do that, and we only updated it on one of these loops, then the execution time drops dramatically. Now we're executing on average 265 microseconds per loop. Next step, we added the PID loop. So the PID loop right now is running super safely with coefficients of 0, 0, and 0, so literally nothing's going to happen. I've included the wire library, which allows I2C communications with the motor shield. I've added the motor shield library, which gives us the handy-dandy commands that allow us to actually talk to the motor without banging our heads against the wall. We have created the object AFMS for the motor shield. I have created a motor connected to the motor shield, and I'm calling it elevator motor. Right now, it's connected to the motor pot, which is on M4, but because I'm using defines, I don't actually need to know that it's M4. I can just say pin motor pot 1 CV, and that's all I need to know. In setup, we initialize the motor shield, and initially I'm going to set a very low speed, a very low power output to the motor just in case, and I'm very specifically going to release that motor, which ideally allows it to coast, certainly takes power away from it. Nothing really changes in loop because we already have this function that's being called on a specific schedule. What did change was that I took the code from the PID demo and I put it into the function update PID. So we're now calculating the error, doing the calculations, creating a new CV, to go to the motor, limiting it to 100%, and then driving that to the motor shield. Now, later on, I may make a few changes to this. I may pull this, the actual activation of the motor, out of this function and give it its own function, because sometimes you're going to want the program to run and tell the motor to do things, and sometimes you're going to want the program to run while not having the motor do things. And it is annoying to constantly come into a function and comment out and then remove the commentary when you're doing troubleshooting. So if we run this program with 0 PID coefficients, as we already know. There will be no output to the motor, regardless of the error. 0 CV. At the moment, I'm not doing anything with the buttons, but the buttons are active. If I give the proportional a 1% per percent error, we get our little jump with lots of error. If I give it some integral, it wipes up the error. An integral of 10 can oscillate. So let's give this an integral of 5, but bump up the proportional to 10% per percent error. And this should be a good starting point. That's pretty damn good, actually. So the next thing I'm going to do is I'm going to introduce a velocity limiting function, and all that's going to do is it'll use the position of the potentiometer as the destination, but rather than have the set point directly linked to the position of the potentiometer, the set point is going to slew at a maximum velocity that I can adjust and set, such that it takes 1.5 seconds to travel between those two LEDs. 1.5 seconds per floor. Okay, so there have been a few changes. One, I am defining the lobby, and I'm defining the top floor as floor 4. This can change in between program runs, but it does not change during the program run. So it can be a constant. And that allows me down here, when I declare the floor calls, the status for the push buttons being called, I can just simply say top floor plus 1. And all of a sudden I will get 5 booleans or 8 booleans or 20 booleans that I can play with. Elevator status exists. At the moment I'm running the PID with a proportional of 10 and an integral of 5. There's no hysteresis, so it does hunt a little bit, as you can see, but it's not horrible. I will take care of that later. We have some new motion control variables. Most of these are not being used just yet, but what is being used is the next position, which is being calculated continuously based on the maximum velocity of 1.5 seconds per floor and the update rate of that particular function. Now that function is called update motion control, and right now I'm updating it every 20 milliseconds. And then we have this function. So the function is a very simple constant velocity shift toward whatever the motion end position is. The motion end position is wherever this is. This used to directly drive the PID set point. It does not do that anymore. This position is the end position, motion underscore end position. And the end position, if different from the current position, will be pushed gradually toward the end position and fed to the PID on every iteration. I am calculating a maximum increment for that position change based on the maximum velocity of 0.67 floors per second times the period of the update divided by 1 second, measured in microseconds. So just with everything else, the maximum velocity is 0.67, but if I'm updating it 10 times per second, then the update is actually going to be 0.067, not 0.67. I only shift the position if the difference between the current position and the next position, the end position, is at least 2 times that increment, because I don't want things jumping around and being super noisy. If I do choose to move, then I move the next position by the motion max increment, and then the PID set point becomes the 0 to 100% equivalent of the floor. Floors being the floors between lobby and top floor. If I change the destination, it moves at a constant velocity toward the destination. No faster, no slower, no acceleration. It just goes at a rate of 1.5 seconds per floor. Now, cool thing is, right now, the floors are here. Here's floor 1, here's floor 2, here's floor 3, here's floor 4, because we have 4 floors. So if you watch the motion, it's going to take 1.5 seconds to move between those dots. But later on, when we want to play with more floors, since I have also in the program made a change to the Neopixel update to take into account the upper floor and lower floor, whatever they may be, I can change the define that says our top floor is floor 4 to something like 7 for 7 Neopixels. There is a little bit of a jump in the PID loop, which I need to deal with later. But you notice that it's moving a lot slower. In fact, it's moving half as fast, because now floor 1 is here, floor 2 is here, floor 3 is here, floor 4 is there, floor 5, 6, 7. Each LED represents 1 floor. But it still maintains the timing of 1.5 seconds per floor. Next step, I'm going to integrate the full elevator logic. So, in case it hasn't been very clear from all these videos, I have a very, very well-developed ability to lose focus, go off on tangents, and go down rabbit holes. So for this last section, I am simply going to demonstrate the current status of the program, and I will attach this program to this video so that you can go through it and look at it. The program definitely has some issues, especially during startup, because I'm not doing any kind of soft start function. I am not delaying the PID and the motor controls until things have stabilized. So when you first start the program, upload the program, reset, there's a jump. There are a few other things that are not super clean, but the overall function of the elevator is there. So the program has been modified. This no longer does anything. And at the moment, the PID coefficients are all 0. The process value is blue. If I press button 3, floor 3 is called. Right now I have all of the 4 floors initialized as being called when the program starts. So if I give the PID the ability to move things around, the first thing you're going to see is the PID jump a little bit because of the current status of the variable. Travel rate is 1.5 seconds per floor. If I request floor 4, it goes to floor 4. If I request floor 2, it goes to floor 2. If I request floor 1 and then floor 4, it doesn't immediately reverse, and if it's on the way to floor 4 and I request 2, it does not immediately reverse. In fact, if I randomly activate all of the buttons very quickly, it's very clear that the code does not allow reversal of the elevator until the floor it's moving to is serviced. Now, the motion code that I'm using is slightly modified from the original, and just as that last thing, if I go to a floor and the elevator is idle for 5 seconds, it automatically sends the elevator back to lobby. Because the eventual motion code is not going to be just simply a constant velocity ramp between floors, but is actually going to have acceleration and jerk considerations. As previously discussed, I don't want the elevator to be called to floor 4, and just before it gets to 3, I call 3 and it comes screeching to a halt. So if it is on floor 1 and we call it to floor 4, it is being sent to floor 4, and it will not change status until it reaches floor 4. Going to floor 1, it will bypass 2 if 2 is called later. Going to 4, it will bypass 3 if 3 is called later, and will not reverse just because. In the code, everything is scaled based on the top floor. So if I take advantage of 7 LEDs worth of travel, and I give top floor 7, floor 1, 2, 3, 4. In the check push button function, I do have a little piece of code that 5% of the calls of this function will result in a random push button press between the lobby and the top floor. And there was a 5-second idle called to lobby. Let's change this back to 4 floors and change the motor that is active to be the full elevator. Proportional 1. And we will turn on the power supply. Motors like power. Proportional of 5. It's actually not too bad even without integral. But let's give it at least a little bit integral. That's not horrible. The important thing being that you can see that it does work. However, the major problem that I can see I'm having right now, springiness in the drive is very high. You have to understand that at the moment I don't have a synchronous belt or a gear drive or a direct drive to the pulley. What I have is a DC motor running literally a rubber band. So the rubber band is making things very jumpy. I will make a few changes to the structure. I will make a few changes to the drive for the next video, which is also going to have some various updates, including more intelligent motion planning. Right now we have a constant velocity system. I want something that takes into account jerk and acceleration and operator comfort. And we also have that DC motor that I made, which I want to also have work with this. For now, this is doing what I want it to do. I just wouldn't recommend being a passenger on it.